So we're going right back to the beginning to start off with good old methods in algebra. One of the first things we learned in algebra, like terms can be added, subtracted, unlike terms cannot. Okay, but it becomes really important because whilst we say like terms and we're talking about algebra, the idea carries through with surds. Because a surd, when you think about it, is an unknown when you don't know what the square root of 2 is. So it's the same sort of idea. When you come through talk about imaginary numbers, I don't know what I is, but we can still use the same ideas, and so it's true throughout all our maths really that this idea. I don't think I bothered with an example for this one. I think we cope okay. So the good old index laws. We know, of course, that when we multiply we add the powers, when we divide we subtract the powers. Parentheses, that's where then we multiply the powers. And then of course comes one of the first lies we tell you, and anything to the power of 0 is equal to 1. Of course that's a lie, because it's not true. Is it? Think about it. Well, if I can find a case where it doesn't work, then it's not true. 0 to the power of 0. It's not equal to 1. See? So, more interestingly, what do these indices actually mean? And when, again, the first time you deal with it, it's a very simplistic thing. We say, oh, this is how many times we're going to multiply the number by itself. And that's great when you're talking about whole numbers and positive numbers. But when you start talking about fractional indices and negative indices, that sort of loses that meaning because, power of -2, I'm going to multiply it by itself -2 times. It doesn't make sense. Okay? So the way I think about it is positive, top of the fraction. I'm on the top of the fraction. Okay? Positive. Negative, I'm on the bottom of the fraction. Or I suppose, more correctly, would be to say positive means keep me on this side of the fraction, negative means put me on the other side of the fraction. It's like a little instruction. So if you've got a fraction with something to a negative power on the bottom of the fraction, then you move it to the top of the fraction and make it a positive power. If it's a positive power, you leave it on that side of the fraction. Okay? Then we have these fractional powers. A over B, what do they mean? Well, the top tells me the actual power, the bottom tells me the root. So even with whole numbers, that's true. Like x squared really is x to the power of 2 over 1. So 2 is the power, 1 is the root. Now, we don't normally talk about the first root of a number, because it's kind of meaningless. In the same way that a number to the power of 1 is, well, it's just the same number. Same sort of idea. X to the power of A on B. Top tells me the power, so it's x to the power of A. B tells me the root, so it's the bth root of x to the power of A. But the actual order you do it in doesn't matter, so you could say, oh no, it's the bth root of x all to the power of A. I guess it depends whether you're dealing with numbers or whether you're dealing with algebra. If I'm dealing with numbers, I'm probably going to do the root first. If I'm dealing with algebra, I'll do the power inside the surd. Main reason for that is it's a lot easier to raise a power to a smaller number. So if you do the root first, if you're talking about an actual number, the number will become smaller and then you raise that to the power rather than go to the power and now you've got a really big number and you're going to find the root of that big number. Rule of thumb, and it doesn't matter of course which way round you go. So x to the -3, hang on, -3, that negative is telling me, put me on the other side of the fraction, because everything, even numbers, there is a fraction there. Whilst we don't see it, there is a fraction there, and that is, of course, over 1. So we'll put that on the bottom, and there it goes, 1 over x cubed. So if I wanted to write that, a to the power of 5 over b to the power of 7. And then we like to, remember this, like we do that, and then we like to make things look hard. And oh my God, look at this, all these terms and what have you. But it's just the same rule each time. The 3/4, you've done the job for me. 3's on the top, 4's on the bottom. Then the x to the 4, that goes on the other side. A to the 9 will stay on the top. B squared goes on the bottom. So x to the power of a quarter. Top tells me the power, bottom tells me the root. So that's the 4th root of x. Y to the power of 2/3. Well, when it's algebra, as I say, I tend to do the root of the power, so cube root of y squared. Other way around, 3 on 2. Now, a mere mortal would leave the answer like that, the square root of x cubed. But of course, I'm sure you're like me, looking at that and starting to get a shiver and go, no, can't leave it like that, because we always simplify our surds. And that, of course, can be simplified. Because the idea behind simplifying surds, if I can write it so that it's a product of a perfect square, I can simplify it. And of course, x cubed I can write as the product of a perfect square, because I could write it as x squared times x. And the square root of x squared, then we simplify the surd and we get x root x. And so of course, the mere mortal leaves it as the square root of x cubed. But us super mathematicians, we would go, no, that's x root x. Okay? Now, how do you spot it? Again, you do something that you never do. You think it, but you don't do it. Right? So you see 3 on 2, right? So that's what you're seeing. But what you're thinking is 1.5. And then it's really obvious. Because what you're saying is, oh, it's x to the power of 1 times x to the power of a half, x root x. And so that's the easy way of doing it. You think of it as the mixed numeral rather than the improper fraction. That tells you the answer straight away, how you simplify that surd. Get something like that, not that you probably will, but say you did. 27 on 4, you go, probably do something like that anyway. But of course, that's 6 3/4. So we get m to the power of 6 times the 4th root of m cubed. Right, so then we try and make it look really hard and just throw everything in there. So the first thing I do is draw. It's a vinculum. Come on, you've never heard of that expression before. A vinculum. A vinculum is the name for a fraction bar. It's called a vinculum. The n, well, that's going to the bottom, end of the 6. 500's positive, it'll go on top. Or minus, it's on the bottom, 1/28th. So that's the 28th root of q. C to the 7 on 6, it's on top. Oh, improper fraction, so 7 on 6 would be 1 and 1/6. So that'll be c times the 6th root of c. And then we just have r to the power of 69, or if you prefer yin-yang. Nice number 69, you've got the yin-yang symbol there. There it is, r to the power of 69. Fractions to negative powers. Well, remember I said the negative means put me on the other side. So rather than working out 2/3 to the negative 2, it's easier to work out 3 on 2 to the power of positive 2. Yeah, you swap the sides around, make it something easier, which is of course 9 on 4. Okay, so there's our first exercise, 1C, and 6A, I've jumped ahead to 6A, I think that's on indices. I just think it's more logical to look at indices now when we're talking about algebra. So I've jumped ahead a little bit there.